radio astronomy to measure the distance. Next slide.
দারুণ দারুণ
Einstein, from the Einstein special theory of relativity and general theory of relativity, we get there the Lorentz transformation and Galilean transformation. So suppose consider two frame of reference. Frame of reference and this is frame of reference and this frame of reference is moving with a constant velocity t with respect to this s frame. So any point with respect to s frame x, y, z, t and with respect to s term this will be h dash, y dash, z dash Yes. So according to Lorentz transformation, we get the equation that, and we know that h dash is moving with v velocity with respect to s frame, and y and z axis are parallel. So h dash is equals to gamma times x minus v, and y, and this transformation will be in linear form, and y dash will be y, and z dash will be z. E dash will be E minus dx by divided and we all know that this is Lorentz transformation, and if the gamma which is 1 by root 1 minus b square by c square, when b much smaller than c, then root 1 minus b square by c square which tends to 1, and this equation will be x prime is equal to x minus dt, y prime is equal to y, z prime is equal to z, and t prime is equal to t. This is Galilean transformation. So from this we get that Galilean transformation is a special case of Lorentz transformation. There is a two related time dilation and length contraction. Consider that frame of reference. This is S frame and there is observer O, and this is H dash. There is observer O dash, and a rod AB is fixed with S frame. And this. So, and A dash frame is moving with velocity v with respect to s frame, and the length of AB with respect to s frame will be x1 0 0 and h and x2 0 and with respect
এখানে বোর্ডে লেখাটাও দেখা যাচ্ছে, এই স্ক্রিনে লেখাটাও দেখা যাচ্ছে। মোবাইলটাতে বোর্ডে কী হচ্ছে সেটা দেখা যাচ্ছে, স্ক্রিনে যেটা আছে সেটা দেখা যাচ্ছে।
According to Lorentz inverse transformation, we all know that x1 prime is equal to x1 minus dt and h2 dash is equal to x2 minus dt So x2 minus x1 x2 prime x1 prime equals to x2 minus x1 divided by 1 by 2 1 minus 1 minus this square by this square.
আমার গিফটেড খুলে গেল
A is equals to a naught by gamma. Here is
আমার মাথা আছে কি
greater than a. This is length contraction. And time relation, and the second phenomenon is time relation. It is the difference in elapsed time as measured by the two clocks due to the relative velocity between them. And time relation, for the case of time relation, we get tau is equal to tau naught times gamma. Tau is equal to tau naught into 1 by that tau will be greater than tau. This is what time is. And our friend Vikram will discuss the next one.
So,
তাহলে ঠিকই আছে
after understanding superluminal motion, we have to understand the apparent velocity. What is apparent velocity? Apparent velocity is generally called that which velocity is not proper the actual velocity of a particle. It is the observable velocity, which is denoted by apparent velocity or speed is distance to object into angular speed. So then some scenarios or cases in apparent velocity we saw with relative motion two cars facing each other backwards or onwards going. So also we saw that in astronomy it is seen and some Doppler effect is seen. Okay. Relation between superluminal motion and apparent velocity. If a jet is oriented at small angle to our side, our observable relativistic effect is relativistic speed combined with Doppler effect can create the illusion of faster than light. The apparent speed can exceed the speed of light, which is called superluminal motion. Then a relativistic jet is coming out center of an angle of active galactic nucleus is moving heavy, and in O we have one is observed this motion. So if the angle phi is very small, so then we get some this angle phi is from position A to B. The galactic active jet is going A to B. Then the initial position to final position the angle is phi from the observer.
O is observer.
Yes, O is observer.
A is the
Initial position of the jet and B is the final position of the jet. Then we after some derivation we get that we get some equations and we have the BT equal to the apparent say I said apparent BT or beta means beta sin theta by 1 minus beta cos theta. Then after if the beta is the maximum velocity of maximum value of beta after the derivation equal to 0 first order derivation, then we get the beta Tmax equal to beta gamma. So this show some special cases. Then we got in this if we take v equal to means the actual velocity of a particle v equal to 0.9, then we see that the velocity of speed of light at distance traveled is much lesser than the particle moving speed of superluminal motion. And if we take the v is very lesser than c, then 0.5, then this will happen that the superluminal motion speed is lesser than for light. That is called not for superluminal motion. It's a apparent velocity. We say. In some or other special cases, if we take t equal to 0.707, that's it happen the superluminal speed or the speed of light is actually same, then the graph is plotting the graph is colliding each other. Then another special case, if we take t equal to very very less than c, then we see that it is a Newtonian mechanics thing, the c is very very higher and e is very very lesser than. So the next part is discuss the minimum intent. What's the box?
So now we are going to tell about some of the observations or applications during superluminal motion. First of all, coming chain of radiation. Chain of radiation was it was actually established by the Soviet scientist called Alexeyevich Cherenkov. The idea he proposed was that in a certain, we know the speed of light c in vacuum is equal to 3 into 10 to the power 8 meter per second. This is the speed limit of the universe. But in a medium, say let's say water, the speed of light becomes 0.75% of c. This is because of a refraction element that is working in water, the refraction index of water. So he said that although the velocity of a particle cannot exceed c, it can exceed this speed of light in water or a medium. By the way, the medium has to be transparent for this one. Let's say there is a positively charged particle or negatively charged particle. This charged particle, when it is in water, it radiates some electromagnetic spectrum for reaction, and although all the colors of the electromagnetic spectrum are given out, we can see that all we can see is blue. This is because that the light which our eyes receive, they are sensitive to blue because the electromagnetic spectrum is at a peak in the ultraviolet radiation range. Now, to give a very crude example of how the spectral radiation works, let's say this is a boat, this is an ocean. This is a boat, and in the ocean, the speed of a wave is c. When the boat is traveling, let's say the boat is traveling at a speed greater than the speed of wave. Then, when the boat is traveling, it gives off a wave of the except water stream that is caused when the boat is going forward. In this, by comparing trend of radiation with this phenomenon, we can say that the particle boat is moving in the medium ocean where the speed of light or the speed of wave is c, and the wave caused is the radiation emitted from the trend of radiation. These are some of the applications of trend of radiation. This can be used to detect high energy particles. Astronomy and astrophysics, it can be used in telescope to locate distant celestial objects which emit that radiation. It can also be used in nuclear reactor monitoring to check on the neutrinos that if they are acting with each other or not. It can also be used in medical imaging to select which cells or which cancer cells the gamma radiation is affecting. That can be done with this. Then remote sensing and medical sensing. Next, after the trend of radiation, we come to the particle which can emit trend of radiation. This is tachyon. When a tachyon moves, something like this happens. Now, tachyon is theoretically is a particle which is only theoretically explained, not explained. This particle this tachyon particle, normally we know that Albert Einstein's equation, normal particles follow this equation. Let us go again. This is the normal one, where if velocity increases, energy also increases, and so does the momentum of the particle. But in case of tachyons, let's say I'm calling T, the equation slightly changes into mc square whole square minus pc whole square. This minus factor has been introduced just to eliminate just so that the conservation laws are preserved. What so according to the theory, the tachyon works in a way like this that if velocity increases, the energy of the particle will decrease, so will the momentum. Now this is theoretically all the applicable, practically this cannot be achieved because it is not possible practically. Because this would mean that as velocity increases, the velocity reaches c, the energy will become zero.
This is rest energy. This is rest energy.
Total energy. Super current. The next comes wormhole. Wormhole or hyperspace is like a phenomenon in space. What happens is when the theoretical proof is when a particle of speed comparable to c goes to the space, it can transfer through a hole or tunnel in the space and go to another separate location which is located in a different space or time length, separate from where it actually was. Now this wormhole, the existence also has not been proved. It is said that when the particle goes to this part, it actually is going faster than speed of light because this if the particle was supposed to reach from that plane to this plane, it had to go from here to here, then it had to come here. But because of the wormhole, if the speed of the light is speed of the particle is comparable to light, it comes from here. So time taken for the particle to come from here to here is less, which is actually a cost, which is actually a result of time dilation and length contraction because of the speed of the particle. Now, the next part of this discussion will be concluded by Peter.
So yeah, so Bokshi already discussed wormholes. So another point of attention of physicists was about phenomenon called redshift. So what exactly is redshift? Like we say there's an astronomical particle at some point in space which is emitting some sort of a radiation. It has some frequency at it. So what happens is like say if I am like assuming I'm at rest with respect to the universe, let's say that there is this particle that's emitting some sort of a radiation. If it moves away from me with some velocity that is comparable to the speed of light, what essentially happens is like we have this Doppler effect that kicks in, and what happens is the wavelength of the radiation actually increases. That actually comes through. Like let's say this is me. This is this particle which is emitting radiation. Let's say for the sake of this argument, this particle is at rest. So essentially what happens is it emits sort of radiation of uniform wavelength in all the directions. Now, if the particle
I was just seeing that's kind of like moving away from me with the velocity v. What essentially happens is it doesn't actually emit wavelength with uniform, it doesn't emit radiation with uniform wavelength in all directions. What happens is it kind of like if it's moving in this direction, essentially something like this. What happens is like the direction which it is moving away from the waves that emitted, the wavelength of those waves actually. So the wavelength increases, that means the frequency actually goes down because the speed of electromagnetic radiation is constant. So what we can do from this is like scientists can actually are able to measure the wavelength or the frequency of the radiation that's actually coming from this source. They can actually predict the speed of the particle. So oftentimes we have actually seen that the scientists have observed that the particles actually appear to move with the speed that is comparable to that or greater than that of speed. Now, is this actual superluminal motion? Turns out it's not. What basically happens is, even though the particle is actually moving away from us, we actually don't take into account the general relativity. That is, like the space is actually expanding. So what happens is like Einstein's theory of relativity and all this, we actually assume like the stacking occurs in relations. So what actually happens is if space itself actually expands, it's not actually the moving with superluminal motion. Space expands, that's why this actually appears to be moving away from us. The actual turn of this actually does not move with superluminal motion. You can actually go to this relativity that we won't be able to stop. So that's so now I'll like to call my friend Vishnu for it.
So before coming to the question part, what is a star? Star is nothing but a astronomical object with a luminous sphere in the galaxy. So there is three questions. Where what is the heat of the star coming from, and what is where the star is stable, and what is the main part of a star? So the thermonuclear reaction inside the star is two hydrogen collapse and react each other and become a helium and emit some energy. So this energy is tons of heat and is ejected from the star, and that's why the star is shining. So this thermonuclear heat energy inside a star was towards the outward, but there is gravitational field also be acts on the star. This direction is inward. These two both balance each other, and that's why a star becomes stable. After this, the life cycle of a star. First of all, the star not appear in this size. So giant gas cloud or nebula. First of all, these transfer to protostar and this Tudori phase. After this, if we consider the mass of sun ms, the mass of sun 1.44 mass of sun times is greater than a star is called the massive star or high mass star, and if the star's mass is less than 1.44 times of mass of sun, then it's called low or medium mass star. So from the massive star it becomes dead. When it becomes dead, the reaction of this thermonuclear reaction is moved to forward, the amount of hydrogen is become decreases. As the hydrogen amount decreases, there is no amount of hydrogen inside the star after a lot of time. So there is no nuclear, no reaction inside the star. All the gravitational force applying on the star, and the star becomes dead. So after that, there is supernova and or planetary nebula. same gets applied on the lower medium star. So in case of supernova or nebula, there is explosion. So after explosion, there is become from supernova to black hole or neutron star. So if I draw a scale of the mass of sun is take that ms if 1.44 times ms of the mass of the star is less than this, we count it as white dwarf or and black dwarf. If the mass of a star becomes 1.44 ms to 3 times of 1.44 ms, between these things, it is become neutron star, and the mass of the star beyond of this is termed as black hole. So from level this is the quasar. In the center of this, it is a black hole, and this is the accretion disk, and the jets coming from the black hole. Not from black hole, the matter will moving from this accretion disk coming with a velocity of 6 to 7 times of light speed. This is not happens in this space because we know that there is no actual velocity of particle more than light. So this is totally optical illusion. This is quasar in the year of 1950. The scientists watched that there is a lot of this star-like structure in the higher space. They termed it quasi-stellar radio sources. Quasi-stellar means star-like, not star, star-like. This is quasar.
Wow.
This is the actual quasar what happens in the universe. Each galaxy has a black hole in the middle of this, and after death of this galaxy, it becomes quasar. Now, how we distinguish a star and a quasar? In star surface, there is lot of atom or ionized particle. So they absorb the wavelength of light what was the emerged from the star, and that's why the spectrum was absorption spectrum. And for the case of quasar, there is no atom like to absorb the light, because that's why these lines are totally upward, not the absorption line. We look in the part of quasar. This is the difference to differentiate between star and quasar. So the closest quasar to us is Marthelian 231. It is termed as also MRK231. So this is the closest quasar. There is two massive black holes revolving each other in this free space. This is the J043947.08 plus 1633415.7. This quasar is the brightest quasar in the universe till now. So we can see that the redshift is 6.51 times the this is a double quasar. This is very complicated to detect a quasar. It is a single quasar or double quasar, but the scientists can identify recently in the year of 2012, I think. The telescope the users are these radio telescopes and Parker's radio telescope. So after this, I call Kazim to continue.
So, as we all know, the speed of light is the universal limit of speed. That is, nothing can actually, like so far we know, nothing can actually exceed the speed of light in that. So, basically, like from the assumption that nothing can actually exceed the speed of light in vacuum, we actually have that theory of relativity and as well as special relativity, general relativity, it is actually based on. So basically, if we actually go to what problems we actually face because of the
means we have the like space travel. Like, say if you want to travel long distances, let's say from Earth to maybe Jupiter or Neptune or beyond the solar system. So that actually takes a lot of time because like we can actually we can only go for limited speeds. Like we can't. So far we have no method to actually exceed the speed of light or even go even close to it. So, if you want to conclude, so I guess we have all have one question, that is superluminal motion actually possible or is it not possible? So like so far I have to say there haven't been any concrete evidences. There have been some misconceptions and some failed experiments and all, but actually no concrete evidences have actually so far shown up that show that actually superluminal motion is possible. However, this is an open topic in the future. We might actually sometime in the future get some particle which actually exceeds the speed of light. Might. We have no idea. So then if that actually happens, that actually opens up a whole new branch of physics. Basically, that means like the entire theory of relativity as well as the principles of relativity, the entire mechanics will actually have to be reworked once again. But so far it's like it holds up pretty well. So again, it's a topic that can actually have some we can actually have some research in the future. So with that, this I would actually like to conclude the presentation. So here is our team. Special thanks to all the members.